آقای دکتر راحت تر بودن که به انگلیسی ارائه رو بدن. اول حالا من مقدمه که به زبان فارسی گفتم، خود ارائه به زبان انگلیسی برگزار میشه و انتهای اون چند دقیقه این دکتر در مورد مسیر آکادمیکشون به زبان فارسی صحبت میکنن و چند دقیقه ان شاءالله پرسش و پاسخ خواهیم داشت. آقای دکتر در خدمت شما هستیم.
با سلام، خیلی ممنون از معرفی بسیار دقیق و سخاوتمندانتون. باعث افتخار هست که در خدمتتون هستم برای ارائه در سری 8 وینتر سمینار سریز دانشکده کامپیوتر دانشگاه شریف. من با عرض اطلاع قبلی به زبان انگلیسی ارائه خواهم کرد ارائه‌ام رو. Today I'm going to talk about decision making under uncertainty with side information. I'm going to skip this. So here's the outline of my presentation. I'm going to talk about motivation of this kind of research. I'm going to introduce one class of problems. I'll get to that. I'll call that data-driven contextual expected value constraint optimization problem. I present some theoretical results followed by some numerical illustration of the results. And then I end my talk with some conclusion and areas for future work. All right, so let me start with the introduction. This is a disclaimer. So the title of the talk is Decision Making Under Uncertainty. There are many frameworks to make decision under uncertainty, such as Markov decision processes, queuing theory, stochastic optimal control, and many more. Today, I'm going to talk about what we call stochastic programming. I'll introduce the framework in a moment. But I want to also say that in many of these classical formulation of stochastic programming, we assume that the random parameters that we have in the model, we know the probability distribution associated with those random variables, which is known to the decision maker at the time of decision making. Another disclaimer is many of optimization problem, decision making problems under uncertainty in practice, in real words, are dynamic, where decision has to be made sequentially over time. In this talk, I'm going to only focus on decision-making problems that are just one-time decision-making problems. We just have some static decisions that we have to make. With this introduction, so this is the class of problems that I want to look at. So I present some mathematical formulation with that, and then I'll look at some application to better motivate this kind of problem. So depending on your background, you may have heard about stochastic programming, and one of the most famous model in the stochastic programming is the so-called two-stage stochastic programming. So in this slide, I want to introduce what I call and refer to as classical two-stage stochastic programming. I abbreviated that with SP. So in this kind of optimization problem, you have a decision maker who makes a decision U, which sits in a set that I have shown with this capital told you. Decision has some cost for the decision maker. So cost or objective function, as in the previous model, we have some deterministic costs. However, the constraints in the problem are stochastic, and the decision maker would like to satisfy those constraints with a high probability. I have shown again the probability distribution of y with this letter P, and we like to satisfy the constraint in the problem, these guys, the g of u and y, with a high probability where this epsilon is the goal that I have of the satisfaction of this constraint. Again, because the uncertainty is there in the problem, we might not know exactly what's going to happen tomorrow. So we just want to satisfy every constraint that we have in the problem with a high probability. Another form of the problem, which is again related, which is something that I call expected value constraint stochastic program, and I refer to it as ACP, has a similar form as the previous model, except for instead of satisfying this constraint with a high probability, we like to satisfy those in expectation. Again, this function g is random, and we want to satisfy this function with a in expectation or an average. We want this to go above some target level of what I call epsilon in a model. So just some few examples. I have background in industrial engineering and essentially operations research and operations management. And what we look at in this kind of discipline is some real applications that could have some intuition and insights for decision-making in practice. So you can think of a decision-making problem in any discipline, but I want to focus on two specific problems. One of them I'll bring it in the talk later on. But here are the problems that I have. Suppose that I'm managing some farm, and I like to know what part of the farm I have to plant. What kind of seeds? Suppose that I have two choices. Either I can plant corn or I can plant soybean. But what I like to decide on is what portion of the farm I should plant on what kind of seed. What part of the plant I should, what part of the farm I should plant corn. What part of the farm I should plant soybean. And this percentage that I write is going to impact my my gain and my total revenue, because the yields of these crops could be different from each other. So in this problem, the decision U is on my decision or strategies on the portion of the farm that I have to plant each of these crops, and the uncertainty in the problem is going to be on the yields of these crops. A more practical, perhaps, problem for many of you is in portfolio optimization. You suppose that you're trying to invest your assets and money on some kind of assets, and you like to know what part of your investment should be on a particular kind of asset. What part of your investment should go to stocks? What kind of your investment should go to bonds? And again, the uncertainty that you have in this kind of problem is that the returns of these assets are very random, and you're going to make a decision today and hope that something goes in your favor and you earn some more money. So, but the decision here is again how to make this decision today, not knowing what's going to happen tomorrow about the uncertainty and the return that all these assets can give it to. So these are just two examples, but you can think of many other problems that you may have in your work. Suppose that you want to go from point A to point B, and you want to find the best possible set of paths that you should take. So you're trying to find some shortest path between 2 points, but in this problem, the travel time on each path is going to be random. So not knowing what's going to happen exactly to this travel time, you're going to make decision at point A with the hope that you get to point B at the least possible time, or you need to travel the least amount of distance. So again, this kind of problem can be formulated with this so-called stochastic programming framework. I mentioned two-stage stochastic framework. I mentioned chance constraint problems. I mentioned expected value constraint problems. Any of these problems can be formulated depending on the goals that you have, depending on the kind of constraints that you have. You can formulate those problems in any of those frameworks, and I'm going to consider this kind of problems that a decision maker in practice has to deal with. Okay, with this sort of long introduction to the models, hopefully they make sense. The argument is that these are classical models. They have been very well studied in the literature. There's so many approaches to handle this kind of problem. Data-driven approaches to solve this problem has been argued. Some approximation algorithm has been developed. People have looked at the consistency and rate of convergence of the approximation algorithm to the true problem, and very well studied. So this is not going to be the focus of my talk. So these are well done work in the past, well studied problem. But what I like to look at is in this kind of setup, in the context of a stochastic programming, is how these models, these classical models that have a history of 60, 70, 80 years, how they can be used in today's data-rich world, where we constantly collect information using sensor, using any kind of technologies that we have. We constantly collect information. So if I want to make, so as you guys are from a computer science, computer engineering background, so if I want to make some analogy is related to what we have in statistics. So in statistics, we have the so-called information that we call context, covariates, features, attributes, independent variables, and so on and so forth, that somehow are related to the random parameter that is of interest to us, something that I showed in my talk with random variable y. So if you notice, in none of the frameworks that I showed you earlier, this contextual information, the so-called covariates or features, had any role in the decision making. So in fact, they were hidden in the decision making, and a usual assumption is that although the return of the assets is random, but somehow we have predicted based on some contextual information that how assets return is going to behave in the future, and based on those predictions, we have took those predictions into the stochastic problem as an input, and just go ahead and look at this problem as if we know exactly what's going to happen in terms of prediction of these assets returns, although the distribution could still be something that we don't know. So that's something that traditional people have overlooked in the stochastic programming, but because this kind of information, this kind of context is available to decision maker, a research question is how we can bring them into the optimization problem directly, in the sense that imagine at the time of decision making, some sort of contextual information, some new covariate information is available to us, and we want to make that decision, again, not knowing what's going to happen in the future in terms of the random parameter of interest y, but at least we have some more information that we can perhaps take advantage of. So in this talk, I'm going to look at this kind of framework that bring in this contextual information into the practice, and I try to bridge the what we call as predictive work to the prescriptive work, to the optimization work. So that's where my talk is going to head to. Now let's bring back those applications that I mentioned earlier. So consider the first problem, the one in farming or agriculture, that the decision maker wanted to know what portion of the farm they have to plant a certain crop. Let's say corn and soybean are the two choices that I have. But I know that the yields of these crops depend on so many other factors, like as weather conditions, temperature, precipitations, the kind of pesticides that we use. These information in the classical model, as I mentioned, they are ignored, or they're somehow hidden, in the sense that one would go ahead and predict the value of y based on the value of x, and then bring that into the optimization problem just as input, and try to solve the problem in sort of separate prediction and prescription manner. In the same sense, in that portfolio optimization problem in the finance application that I mentioned, the returns of the assets could depend on so many other factors, including oil prices, the news about war, unemployment, the war itself, so many other factors can impact how the stock market is going to behave, or financial market in general is going to behave. And what we like to do is, again, instead of predicting this value or the returns of the assets based on these independent or covariate or contextual information, we like to bring them into the optimization problem directly, so that we could have sort of a joint prediction and prescription, or something that I call as joint estimation and optimization, or joint learning and optimization framework. Hopefully this kind of example will give you some idea about the kind of problem that we can handle. So these are, again, just a few examples. The examples and applications are abundant in many disciplines, in engineering, in business, in economics. You can think of these real decision-making problems where the goal is to come up with some decision in the sense that will help people about their decision. I'm not going to be focused about making predictions. So I'm not going to decide whether this a particular picture is a picture of a cat or a picture of a dog. I'm not going to predict whether a financial institute is going to fail or not. What I'd like to do is to bring those information and try to see how much I should invest my money in, how much I should, or how I should take or get to from a point A to another point B. So I'm not going to predict the travel time. I'm going to really know what kind of actions I should take in order to get to point A to point B. This is the kind of problem that we in industrial engineering or operational research in general we are handling, and that's why I focused on my talk in this kind of applications. As I said, feel free to pick any applications that you're most comfortable with throughout my talk, so that you can resonate and relate. All right. So with this introduction, so now that we know the caveats and weaknesses of the classical models and about what they do not consider, so we'd like to answer how can we leverage this kind of contextual information based on some historical information that we have on not only on the context, but also on the random parameters that are on the dependent variable or random parameters that are of interest to us, and how we can really include them into the optimization problem, so that we can make some data-driven decision for our problem. Okay. Throughout my talk, in most places, I'm going to assume that we have a pair of data. So what I call as X, which is going to show the context, and what I call as Y, which is going to show the dependent variable. And I assume that I have a set of N data points that somehow have been generated for me, and I have access to them. All right, so a little bit back this something that I call as joint estimation or joint learning and optimization. This is an emerging topic in learning and in optimization society. People are looking at this kind of problem. So there's a literature in simulation optimization, a well-known framework, conditional ranking and selection has been studied. It's there's so many other topics under the name of end-to-end learning that again integrate between prediction and prescription. If you're familiar with Markov decision processes or any other reward type decision processes, those ideas about joint estimation and optimization is there. And there's so many other terms that people have used, not only into learning, but some other names or terminologies like as decision-focused learning, cost-over-loss function, predict then optimize. This kind of framework has tried to somehow integrate between prediction and prescription, and the work that I present is one work in this whole jungle of the work that are looking at different aspects of learning and optimization, or trying to integrate between prediction and prescription. All right, so so now that I have introduced the two stages stochastic program, and I have motivated, hopefully, that this kind of contextual information that we have could be helpful. at the time of decision making. So it's good to look at the formulation again and see if we want to bring in those contextual information, how the formulation is going to change. So if you remember, I had this two-stage stochastic program where in the first stage I made this decision U, and then whenever the uncertainty Y was realized, I had a chance to make some other additional or recourse decision in order to improve my decision at the first stage. So now if I want to bring in the context into the picture, all I need to do is just look at the context X and just look at the expectation of Y, given that I know that this covariate or context has been observed. So the dynamic of decision making has changed from the classical to a stage problem. In the classical to a stage problem, we make a decision, U, and then tomorrow the uncertainty realized, and then we have a chance to make additional decision or some recourse decision that I have called as V. My apologies, this is a typo. This function F here has to be capital letter G. But now that I have bring in context into the picture, the dynamic is going to change. So at the time of decision making, I have access to some contextual information that I have shown with this letter X. I make a decision U, and then the uncertainty realized, conditioned on the context, and then we have a chance to make a recourse decision in the second stage of these variables that I have shown with letter V. And that's how I can formulate this contextual two-stage stochastic program, which look very similar to the classical model, except for now I have to look at some sort of conditional expectation, condition on what Y will be given X. We are going to evaluate the loss of decision making. Very similarly, if I have a contextual chance constraint stochastic program, instead of looking at the satisfaction of the constraint with a high probability, I have to look at conditional satisfaction of this constraint with a high probability. And again, similarly, when I have this sort of expected value constraint in the problem, I need to look at the satisfaction of them with respect to a conditional distribution of Y, given or condition on that we know what X is. So in this talk, although I introduced these three frameworks, which I can make them even more generalized. So in today's talk, I'm going to focus mainly on this last model, contextual expected value constraint problem, which I refer to it as contextual ECP. And later on, I say that we can even look at contextual CCP, and whatever that I present in this work is going to be applicable to that framework as well. Just for some of you who may pay attention, though I know that the probability of some event can be written as the expected value of its indicator function, which will make this contextual chance constraint stochastic program just a special case of this last model contextual expected value constraint problem by just taking this function G as the indicator function. We'll get to the chance constraint problem just by that simple change of functions. All right, so I'm going to focus then on the contextual expected value constraint problem because it also consumes subsumes the contextual chance constraint models as well. All right, so this is about the framework. So now that we know what the framework is, what the problem is, it would be good to know that how we can really handle solving this problem, because formulating problems one thing, but being able to solve the problem some another things. So again, this is the framework that I'm going to look at. So I have some deterministic objective function that deterministically connects f to this variable u, and then I have this so-called expected value type of constraints that is going to ensure that in expectation we have some lower bound of epsilon. So you can easily see that this is an optimization problem that is being parameterized by this context x. And that's why I'm going to denote the optimal value of this problem with some value that I call it as z star, which is going to be a function of the context that I showed with a little case X here. And of course, because this is a parameterized optimization problem, the optimal solution or any minimizer of this problem itself is going to be a function of the context X as well, which I denoted with this U star of X. Okay, so now if I want to solve this problem, I have to deal with some sort of challenges that that exist. So first of all, so this is the expected value of some functions, and this y itself could be multidimensional. Then that means that I should be able to somehow calculate some multidimensional integrals or multidimensional summations if I have some sort of discrete random variables or discrete distributions. And the caveat here is, in practice, we do not know, even if I can calculate this integral, the caveat is that in practice, we do not know the conditional distribution of y conditioned on x. We do not know the joint distribution of x and y either, so that means that we cannot even know the conditional distribution of y and x. And not only I should be able to calculate whatever this expected value is, I should be able to find the best possible answer that minimizes this objective function. So not only calculation of this is a problem for me, but also optimization is going to be another big thing that I have to take care of. And unfortunately, we do not know this distribution in real line. But what we have is a set of historical data that is available to us, and hopefully we can use this kind of historical information that, as I mentioned, that are appearing in a form of pair of data in both x and y, and hopefully we can make these historical information to estimate somehow this expected value. So again, the dynamic of this problem is that I observe a new covariate that I called x. I have to make decision u, but still I do not know what's going to happen to y. Still y is uncertain, conditioned on x, and that's the problem that I have to deal with. All right. So as I mentioned, that this calculation of the expected value is hard. It's complicated. We have to deal with multidimensional integral, but a very well-known approximation is practiced. What we call a sample average approximation has been proposed in the literature for classical expected value constraint problem. So we do not know the distribution of uncertainty with certainty, but we can have some information on the random parameters of interest, and I can just replace the expected value with some sort of empirical average or empirical sample average, so that I could have some estimation of the expected value. This is your well-known estimator of sample average, which estimates the mean or expected value of some distribution, and I can easily do that so that I can get to some approximation of the problem, and hopefully I can aim for some good result, because I know that by the law of large number, or the more data points that I have, this approximation of expected value is going to converge and get closer and closer to the real expected value, and hopefully whatever that I solve is going to be a good estimate for the real solution. And so this is a well-known estimation, and I want to use the same idea in this talk as well. So I mentioned some examples about the inclusion of a covariate or context into the decision making, and I argued in words we have to do it, but I never really showed you why this is important for us to look at. And here's one example. So consider the portfolio optimization problem that I mentioned. So suppose that I have two sets of assets, stocks and bonds. So I need to put 100% of my money on either stock, on the bond. So I want to have this kind of choices between the stock and bonds, in the sense that the whole money is invested on either stock or a bond or a combination of them. So that will make my feasible set of actions, the set of feasible actions as this. And what I want to solve is that I want to maximize my return of investment. And suppose that this vector that I have shown with y bar is my nominal return of the assets, because I want to maximize the expected return. That's what I would have. And I want to ensure not only I maximize my return or yield on average, but also I want to ensure that my return with a high probability goes above some lower bound of what I have shown as gamma, which is a value of 0.8. With 90% chance, I want to ensure that my return go above 0.8, and only leave 10% of deviation from this kind of constraint. I suppose that that's my setup, and I know from some data that the return of my assets follows a multivariate normal distribution with a mean that is known for me. But the covariate metrics of this multivariate normal distribution depends on the context. Suppose that I have a context that tells me whether we are in a regular market situation or we are in a volatile market situation. And let me denote them with this value of 0 for the regular market situation and a volatile market situation of which I have denoted with 1. The covariance matrix depends on the market status or market situation, and as you may see, the correlation between the return of stocks and bonds are the same in both market situations, but there's a higher variability when I am in a volatile market situation, and I have a smaller variability on the return of either of these stock or bonds assets when we are in a regular market situation. Right. So suppose that that's what I know, and I have took some samples of this distribution. Let's say I have 10,000 samples. I have sampled 5,000 of those data points in a regular market situation, and the other 5,000 in a volatile market situation. And I solve my problem with this sample average approximation that I introduced earlier. And this is going to be my optimal decision. 58% of my investment is going to go to the first asset, to the stocks, and the 43% is going to go on the second asset, on bonds, and I get a return of 1% on average. Okay, so that's how I would have handled the problem if I had not considered that this context or this kind of market information is important at the time of decision making. So, but my real problem is that imagine that I know the world situation, the market situation is volatile, and I want to really know what kind of information, what I can use in order to make the best possible decision. It turned out if the market situation was regular, the solution that I obtained here, 57%, 43% as the combination of investment, is a good decision. It performs well in practice in the real world if I apply this to a real world situation. However, for my real problem, when the market situation is volatile, the solution that I obtained above is not a good solution because it is not going to satisfy my chance constraint. So I was hoping that my return goes above 80%, 90% of the times, but it turns out, well, this solution doesn't have a chance of satisfaction of 90% or above. It has a chance of satisfaction that is below 90%, which means that this solution that I have obtained, it's not even feasible for the decision maker that has this kind of risk perspective about decision making. So hopefully this example shows that if you ignore the kind of contextual information, as I did with the SAA problem, so you may get a solution that may be very well not be even feasible and implementable for the real problem that you have based on the risk preferences that you have. So hopefully this motivate that the kind of contextual framework is the one that should be taken into account. All right, so if you're convinced that, hey, this is the framework that someone should look at, contextual information are important, it's a different problem than prediction because it's a joint combination of estimation and optimization, then we are at the same page and we can look at the literature of looking at or handling this kind of problems. There's a huge literature in statistics which has moved to optimization, the so-called empirical risk minimization approach that tries to somehow jointly look at estimation and optimization in order to find some solution map which maps the context to some kind of a decision. This kind of approaches has been looked at in the past. So this is one way to look at this kind of contextual information, borrowing ideas from statistical learning. Another way of looking at this problem is that we hopefully should aim for a better predictive model that learns this random parameters y given the context that we have. And again, this kind of approaches has been looked in practice. So one way of looking at this problem, as I mentioned earlier, was perhaps use a regression model to try to find a prediction of y given x. Well, that leads to a separate estimation or optimization, but instead, maybe we can look into the structure of the problem and the optimization problem that we have and use a loss function that is related to the problem in the regression analysis that we do. So instead of the so-called L2 norm that we use in regression, so maybe we can look at a loss function that is related to the optimization so that we can find a better estimation or prediction of y given x. So this is another approach. And the other approach is perhaps try to better learn not the values of y given x, but the distribution of y given the context, because at the end of the day, because I need to take the expectation of some function with respect to y given x, I should know the distribution or somehow estimate the distribution of y given x. And that's another approach. And there are many work in this area. And the work that I'm presenting also belongs to this category of work. All right, so I'll go a little bit faster. So the rest of the talk is going to be a little bit more on the mathematical side, but I'll try to convey the big picture idea. All right, so again, so I want to aim for a good estimation of the conditional distribution of y given this context that I have. Hopefully, as the number of data points that I have access to, as those data points increases, I hope that my estimation of the distribution of this conditional distribution converges to the two distribution of this variable. So I assume that I have a set of historical data and I want to estimate that probability distribution. And what I'm going to do is that I'm going to borrow ideas from machine learning. I'm going to borrow ideas from statistical learning. And whenever I want to estimate this probability distribution, I want to estimate it in a sense that given the context that I have observed today, given the x that I have today, I'm going to allocate a higher weight and importance to the data points whose covariate component or whose context is closer in some sense to the context that I have observed today. So remember that there are a bunch of contexts that I have observed in the past, and they can be close to the today's context x, or they could be far from it. So the way that I'm going to find this estimation of the probability distribution is that I'm going to allocate a higher importance to those data points whose covariate component is closer to the component of the covariate information that I have today. And instead of uniformly allocate a weight of 1 over n to them, perhaps, I'm going to allocate this weight in the sense that it puts higher importance on those data points that are somehow closer to today's context, with the hope that this is a better estimation of this random conditional random variable. And I'm using this this notation W to show that importance. I'll talk about it. And the moment that I come up with this kind of estimation for the probability distribution, then I can estimate my expected value in this manner. So this is the guy that I have to take expected value of, and I'm going to look at the expected value with respect to this sort of distribution that I estimated, where instead of 1 over n, as in the sample average approximation model, I use this weight function that varies. It could rise based on x, it could rise based on the data that I have access, and it could rise based on the current context that I have access to. Right? So I said I'm borrowing ideas from machine learning and statistical learning to come up with these weight functions. And here's some examples. Maybe I could come up with this weight function based on a k-nearest neighbor algorithm. So I'll look at my covariate space, and if there's a context that in my data point that is close to today's context, I'll look at the k's nearest one, and I put a weight or importance of 1 over k to all these data points, and I ignore the rest of data points in when I do the estimation. I may use a classification or regression tree or card when I put a uniform weight on all data points that belongs to the same leaf node as the one that the current context belongs to, and I ignore the rest of them. Or I may use look at some ensembles. Maybe I can look at the random forest of these classification and regression trees when I do averaging over different trees. So I can look at different weight functions in order to come up with this weight, with the hope that they give me a better estimation of the conditional distribution. Here's one example. I'm going to skip that. And so this is how I will create my approximation. This is an approximation that I have. So I'm going to a little bit look at what's going to happen to this approximation very briefly, on what kind of insight we can obtain from this approximation. So again, if you remember my original notation, this is the constraint that I had in the problem. This was what I had. And I wanted to estimate this expected value on the left-hand side with some data-driven estimation, where I estimated this expected value with this guy, where I'm using this weight function that I defined. Okay, so depending on how what is my favorite machine learning algorithm is, I have came up with this algorithm with this weight function, and this is my estimation of the constraints. Right. So this kind of estimation, it's going to impact the set of actions that are feasible for me. So the so-called feasible region of the original problem is this kind of set. So my decision has to be constrained in the way that this expected value goes above epsilon. That is my true problem. I'm going to denote it with this notation, just showing that it has dependency on x. It depends on my target, epsilon. But the one that I approximated is going to take this form. So I have estimated my expected value with this guy, and then I'm going to restrict my actions in the sense that I'm only going to look at a bunch of actions that has this property. And I'm going to have some approximated, if you like, feasible region that depends on the target level that I'm going to consider, that I call it alpha, and then it also has before it has its dependency on the context. Okay. So now that I have done this, I have done this estimation. As many other approximation schemes, I need to know how good this estimation is, in the sense that whether it gives us consistent solution or not. Okay. So as a matter of fact, I want to know if I solve that problem with that estimation, and I get some optimal value as a result of solving the problem with that estimation, whether the true optimal value is going to somehow have some relationship to this approximation optimal value or not. I want to, with a high probability, make sure that the true optimal value is going to be bounded below by this approximated optimal value that I have as a result of this estimation. And if I can obtain some probabilistic guarantees on this, that is going to tell me if I want to ensure this statement to be true with some high confidence on of 1 minus rho, how many data points I should have in order to guarantee this kind of consistency, so that I can have some finite sample guarantees on the optimality of the estimated solution. In a very similar sense, I may be interested to see whether the estimated feasible region somehow is contained in the true feasible region or not, because that's a good idea for me to know whether the solution that I solve as a result of estimation or approximation is going to give me a feasible solution or not with a high probability, so that I could avoid this kind of situation that I explained in my simple portfolio optimization. I want to ensure that the solution is going to remain feasible to the true problem. And again, if I have some probability guarantees of this form, I can ensure how many data points I would need so that this inclusion of these two feasible regions happens with a high confidence of 1 minus rho. Okay. So, well, of course, I want to analyze this kind of guarantees, and I need to use some mathematical tools in order to be able to do that. And the tool that I'm going to use is very related, if you're familiar with this kind of inequalities, which referred to as Hoeffding's inequalities. It's a kind of concentration inequalities that shows the tail probabilities that some random variables are concentrated around the mean of those random variables. And people have shown that this tail probabilities has some exponential decay, that the decay depends on how far in the tail we are looking at, this T guy, and how many data points we have. This is a well-known result. And if I can use a form of this kind of result, then I should be able to obtain some sort of probabilistic guarantees on the problem that I have. So this classical result, which has application in many areas of statistics and information theory, unfortunately, it's not directly applicable to our framework, because instead of this 1 over n or averaging that is done here, I'm using a weight function which may not be very well uniform. So it's going to impact the kind of guarantees or tail probabilities that I get. Anyways, I'm going to build up my own probabilistic guarantees, and I'm going to come up with some results that are completely distribution free, completely are not considering any relationship between the independent and dependent variables. All right, so here's the general idea. Instead of assuming that those kind of inequalities are available to us, I'm going to make an assumption that the weight functions that I have chosen based on the method that I have used, it's KNN, CART, random forest, whatnot, it's somehow it's created in a way that uniformly the estimation of the expected value and the true expected value are going, the probability that the estimation of the expected value and the true expected value are further away from each other. This amount of kappa, that probability is going to go to zero exponentially fast. Okay, so meaning that as the number of data points are higher, this expected value that we are estimating is going to be closer to the true expected value with a high probability, where this probability goes to 1 exponentially fast. So I have some sort of exponential growth in order in the convergence of these estimations to its reality. So this is something that I'm going to assume, but fortunately, I can show that for many or a variety of weight functions, this exponential decay can be obtained in closed form. Okay, so if I have this kind of exponential decay, so instead of that Hoeffding inequality that I showed you earlier, I can use my own result, and fortunately, these are available, and I can obtain them. So with that kind of guarantees on the decay of the estimation of expected value to its truth, I can guarantee that with a high probability, the optimal value of the estimated problem is going to be lower bound of the true problem with a probability that goes to 1 again exponentially fast, which is a good result. So as the number of data points increases, I can guarantee that I have a consistent solution. Similarly, I can show that the feasibility of the problem is going to also be there. With a high probability that again depends on the context and whatnot, I'm going to get to a feasible set that is going to be contained in the true feasible region with a high probability that goes to 1 exponentially fast. So I'm not going to go over the details. So there's so many parameters here that are that need to be precisely identified in terms of what epsilon is, what kind of approximation I'm using, what kind of guarantees I have on the satisfaction of the constraint and whatnot. And here I assume that the set U that have been looked at is a discrete set, but I can generalize those results to the case that U itself is not a discrete set. It could be in infinite set, but as long as that set is a bounded set and I have some sort of Lipschitz continuity on the function that I'm looking at them in the constraint, again, I can guarantee that with a high probability, the feasible region that I have as a result of my estimation is contained in the true feasible region with a probability that goes to 1 again exponentially fast. Again, I'm not going to go over the details of what this function A and B are, but depending on the kind of machine learning algorithm that I use, the rate of decay or the rate that this probability goes to 1 or grows to 1 is going to be impacted. And there are so many other parameters that impact this rate of convergence. One is the dimension of my set U that is going to impact that, and many other parameters, including the dimensionality of the covariate space is also another important factor that comes into the picture, and that's hidden under this parameters A and B. Okay, so if I have this kind of result, as I said, I could obtain some minimum data set size in order to guarantee with a high probability we have feasibility. And here's the gist of results. So if I have used k nearest neighbor, so this result tells me that I would need a number of data points that is going to linearly depend on the log of the confidence or inverse of the confidence that I have. It's going to linearly depend on the dimensionality of the feasible region. It's going to impacted by the dimensionality of the covariate space and many other terms that are appearing in one form or another that are going to impact the rate of convergence. So I mentioned some of these results, but I want to make a few points again. So the results that we have are distribution free. I didn't assume that we have a kind of distribution already known to me. Any kind of distribution could be there. I didn't assume that there's a perhaps linear relationship between X and Y, like what we do in the regression analysis. Those kind of assumptions were not there. So I could look at many forms of expected value constraint stochastic problems. One very famous or well used sort of model in practice is the so-called conditional value at least kind of models that have some expected value there. I mentioned chance constraint problems are also a special case. Somewhere in the statement or in obtaining those results, I assume that I have independently and identically distributed data, but that can be relaxed as long as I have identical data, and even if those data are not independent, perhaps have some other forms of dependency, I can still obtain those results. And all the results that I mentioned were in a uniform sense when the case that it was unrelated to the context, but I could also make those results in a point-wise sense as well. All right, so that's the end of what I wanted to talk theoretically, and very quickly I want to look at some numerical illustration of the results. We have developed this theory and for this kind of framework, and we like to see how good it is in practice if we use this kind of framework. And for that, I'm going to look at again at a portfolio optimization problem where the goal of the decision maker is to minimize risk, which is the objective function here, and the constraint that the decision maker has is that it has to invest all its money on some assets, very similar to the simple portfolio problem that I had. And at the same time, the decision maker wants to satisfy that the return is going to be above some target level epsilon in expectation. This is a very well-known model in portfolio optimization. It goes back to 1960s, so-called Markowitz model in portfolio optimization. This is the model that I'm going to look at. So some notation that I have, as I said, D of U is going to denote the number of assets that I have, and D of X is going to be the number of covariates that are going to indicator of what is going to be returned, this random return of Y. So I create some experimental setup in a very synthetic way. So I assume that the contexts are a bunch of random variables that are normally distributed. The return is going to be linearly dependent on some variables. There are parameters that I have considered for this linear factor model. E that depends on some noise parameter, depending on how I could estimate this matrix A, this linear factor model. There's going to be some range of these variables. Some other variables, there's some noise parameter again here that again depends on this parameter that I have called it tau, and A very important part of the model is this guy, this y bar, that each element of this guy is going to depend on the context. This is what makes my dependent variable dependent on the context, and it's going to depend in some polynomial form to this parameter p, which is the degrees of the dependency between this context and this variable that I have shown as y. So I'm going to look at this model. I'm going to generate some numbers from this simulation. I'm going to look at different sample sizes, different values for the target level, different noise level parameters, different degrees of this polynomial, whether this polynomial is of degree 1, it's linear, or it's of higher degree. Then I'm going to do some training, and then I'm going to do some validation based on some test sets, and then I'm going to compare the result and see how the rate of convergence is going to get impacted by changing in any of these parameters. The first thing that I want to highlight is how the dimension of the covariate variable are going to impact the rate of convergence. I've looked at 3 different values for the dimensionality of the covariate space, 5, 10, and 100. And I'm going to compare the models in the case that the degree of this polynomial is 1, this noise parameter is 1, and the target is 10%. We want to have a return of an average 10%. Okay, and then I'm going to compare 2 different models. This model where I refer to as KNN, which is the one that uses a k-nearest neighbor to form the weight functions in order to estimate the probability distribution, and the other one is what I call as naive sample average approximation, which is the one that ignores the contextual information. And then I have these figures, and the x-axis is showing the number of data points that I have. The y-axis is going to show the satisfaction of the constraint. So the higher is the better, and if that satisfaction goes above 10%, we have a feasible solution. So ideally, I want the y-axis to be above 10%. And here are the models. This shows the box plot of the left-hand side of the constraint. You can see that the SAA, the blue box, is not consistent, but we see that as the number of data points increases, this estimation based on k-nearest neighbors gets better and better, and it grows and gets closer and closer to 10%. So as the number of data points increases, I know by my theoretical result that I have to get to a feasible solution with a high probability, and that's exactly what's happening in this figure. Any of these figures from left to right are showing some dimensionality of the covariate. I have a higher rate of convergence as the dimensionality of the covariate space is smaller, but as the dimensionality increases, I have a lower rate of convergence, which is again is expected by the results, that the rate of convergence is going to depend on the dimensionality of the covariate space. We can change the degree of that polynomial model. Instead of 1, we can look at 4 and 8. And again, we can see that as the degrees of this polynomial gets more complicated and it goes higher than 1, instead of linear, it becomes nonlinear, the rate of convergence is also going to get impacted. We will have a lower rate of convergence. And another factor that I was interested in was this noise level. And again, we'll see that again, KNN is having some consistency behavior, whereas sample average approximation has no consistency. And we see that as the noise level increases, we have more variability. These boxes are getting get expanded and gets larger, which is impacted by the variability that we have in our data. But the good thing is that in any case, in all of these cases, the approximation based on KNN resulted into a consistent result. So let me skip this. With that, I'm going to talk about what I, or summarize what I talked about. So I talked about bringing in and including contextual information in stochastic programming. I presented theoretical and numerical results on consistency and finite sample guarantees to ensure feasibility and optimality as the number of data points grows. I showed my result on a portfolio selection problem. I skipped this last part, which was about a team selection problem with application to soccer, or sorry, to football. And I showed a portfolio example on expected value constraint with some synthetic data. If you're interested, you can look at my other work that is published in this journal, Computational Economics, which will look at real data. And we look at a framework that shows that this contextual information have impact for decision-making problem. The work that we presented is that, in fact, is being used by a company, a financial institute that manages $500 million of assets, and they have got many good results by using our methodology for the investment of their customers. So many other things can be included in this work. So this is a very preliminary work that I mentioned. So I didn't look at the dynamic case. We can look at the case that we have sequential decision making. One of the areas that I'm very active in is the so-called distribution robust optimization. Here I didn't even look at that. So I assumed that whatever those weight functions are, they are the reality, I can use them, but it could not be the case. There might be some noise associated with those weight functions. One can try to robustify with respect to those noises as well. And I mentioned the application portfolio selection with some real data, synthetic data, but the applications of this kind of framework are abundant. They can be used to many emerging topics in energy and disaster relief type of efforts as well. With that, I'm going to end my talk. I will be happy to take any questions if you were interested. This QR code shows a link to a paper that most of my talk was based
on. Thanks, Dr. Thanks, Dr. Rahimian. I would like to express my gratitude for your excellent presentation. Since I know that you are going to have another meeting in 5 minutes, I will just ask one of that questions.
Yeah, I can say a little bit longer. So
okay.
I postponed that for another 15 minutes.
Okay. At the last of your presentation, you said about an application of portfolio selection. I have a question about contextual information in that application.
Yes.
What kind of data?
Okay. Great questions. That's a great question. So the synthetic work that I presented, so everything is synthetic, right? So you see that I didn't even mention anything about this X. I just said this is coming from some distribution, right? So this was synthetic. It had no real meaning. But what I wanted to do was to show that these theoretical results are working in practice, and they did. So in this other paper that I mentioned, I skipped this. This paper will look at real covariant information. If I'm not mistaken, we looked at the three important contexts. One was unemployment, one was real estate situations, and there was another one that I do not have in my mind. But if you look at this paper in details, we have listed all these covariant information that we are looking at. Unemployment was a big factor. Real estate situation was also a big factor that was showing dependency on where the assets written were showing dependency on it. And there's another factor which I do not have in my mind, but that was also coming from some economical data that we have.
Yes, I see. Thanks for your answer. I have another question. Is the use of contextual information in the decision-making process being done for the first time? And if yes or if no, I wanted to ask unemployment, real estate, and other contextual information, is that public for other previous works or not?
So,
you collect that for your portfolio selection, or it was released in public?
Okay, sure. So I didn't get the first question. Can you repeat the first question one more time?
Is the use of contextual information in decision-making process being done for the first time or not?
Okay, sure. No, so by no means this is the first time that people are including contextual information in decision making. So in fact, it goes back to some work in 2010, but in the past, I would say few years, in the past 4 and 5 years, this has become a very hot topic in operation research, that inclusion of contextual information and its theoretical analysis has been attracted more and more attention. And our work, which started like 4 years ago, is one of those work, and there's a whole new bunch of work that are coming pretty much every month in this area. But the analysis are sort of, I would say, new, but the idea has been there, but not really in a rigorous way. And I mentioned a few of those work in my literature sort of review. So that's the answer to the first one. About the second question, great question, those information. So because we are looking at the portfolio optimization, stock markets, I would say that no information in real world is more public than information about the stock markets. All those information are available publicly. Everyone can access to those kind of information. So that's the best, I would say, test bed for looking at this kind of decision-making framework. For many other applications like these ones that I have mentioned in energy disaster relief, which is some emerging topics in industrial engineering and operation research, the access to these contextual information is much limited. So, but for stock markets and investment markets, the information are pretty much publicly available, and there's so many repositories that are collecting and storing this kind of data, and we use some of those.
I have another question, and I think it's the last question. Okay. How does the performance of your proposed model scale with the dimensionality of the contextual information? And are there any strategies to mitigate the potential challenges associated with high-dimensional data?
That's again a great question. Absolutely. So as I showed in the empirical results, you see that the dimensionality is going to impact the rate of convergence. How this rate is being impacted, it depends on the kind of machine learning algorithm that is being used for the estimation purposes. And let me go back to these results. You see that I'm showing the result for this k nearest neighbor, and you see that the dimensionality is appearing here in a polynomial form here. So it's there. So I have another factor of dimensionality here. I have another factor of dimensionality of the covariate space here as well. So the impact is there, and it appears that although it might not be a clear-cut impact in terms of being linear, log linear or not, but the impact of the dimensionality is there, and the general sense is that the higher this dimension is, the slower the rate of convergence. So in this work, I didn't mention anything about a reduction in the dimensionality of the covariate space, because as you mentioned, this is going to very well impact the rate of convergence, and that could be a real practical challenge. But the ideas on dimensionality reduction and feature selection that are well known in the statistics can be done here as a pre-processing steps as well. Okay, so all those ideas on feature selection, dimensionality reduction, looking at principal component analysis, and all those stuff can be done in practice. And as a matter of fact, that's what we did in our real world portfolio selection paper. So of course, there's so many factors that are impacting the returns of assets, but as a pre-processing step, we did a feature selection. We did principal feature selection to reduce the dimensionality of the covariate space in order to avoid this computational challenges in terms of the rate convergence later on.
Thanks again, Dr. Rahimian. It was an honor for me and WSS that having you in our 8 seminars. And thanks again. Sorry, if you have last sentiment, I will hear that.
Thank you so much for the invitation. I enjoyed presenting my talk to your group. Also, I didn't see them, but hopefully it was informative. They could get some ideas from this kind of work that it was done here. So I could think that the framework perhaps may not be the framework that many of your audience are familiar with, but at least I could try to convey some ideas about how decision making, how optimization as a tool, and estimation prediction as another area could have a bridge and could be integrated in order to improve decision making in real world. So I wanted to make a distinction that which is the distinction between prediction and prescription, and hopefully I could convey that idea. So if there's one message that I can give to your audience out of this talk, is that prediction work is separate from the prescription or optimization work. They all have their own strengths, and we can get the best of these two words by combining them in order to make better decisions for real world decisions. So our problem is not about prediction. Our problem is not just about using synthetic data. It's about how to use real data that we are constantly collecting day by day, second by second, hour by hour, in order to make better decisions for engineering, operational, and business problems.
Thanks again, and bye. Thanks.
Yes, thank you so much. من دوست دارم که این چند جمله رو به زبان فارسی بگم. بازم تشکر میکنم شما بابت دعوتتون.